So the paper I will present today is the implementation of different image edge detection algorithms in a real embedded ADAS platform. So in the first chapter, I will talk about ADAS and edge detection in general. Then I will cover the algorithms and the ADAS implementation itself. And then I will cover the evaluation of the solutions and conclude the presentation with a conclusion about usability in real-time systems. So as research has shown that driver error is the main cause of traffic accidents, the aim of the automotive industry is to reduce the driver's role in traffic by implementing ADAS, or advanced driver assistance systems, in modern automobiles. They rely on processing sensor data in order to make autonomous decisions, quote unquote. So the key sensor that is related to this work is the camera, as edge detection is an important step in processing images from cameras. So in general, edge detection can be defined as finding abrupt changes in brightness in digital images, as these changes in brightness usually correspond to borders between different objects. And when an image is put through an edge detection algorithm, the resulting image contains less data, which makes it more usable for other image processing algorithms, such as object detection or lane detection. Now, common methods include the Sobel, Prewitt, Laplace and Canny operators, which were implemented in this work. The Sobel and Prewitt operators rely on two convolutional matrices to find edges, one in the x direction and one in the y direction. And then the final magnitude of the edge in a certain point is calculated as a square root of the sum of squares of the x and y edges. The Laplace operator, on the other hand, only uses one matrix, which is used to cover both directions simultaneously. The problem with these methods is that their output images are gradiental, and they have many lower and higher pixel values, which can make it difficult to tell which edges are usable. And that is solved with the Canny algorithm, which uses Gaussian blur, gradient determination, gradient direction determination, and non-maximum suppression and double thresholding in order to find true edges, and it results in a binary image where a certain pixel can either be an edge or not an edge. So regarding the implementation on the ADAS platform, the C programming language was used, and along with the tools from the Vision SDK environment. And finally, it was implemented on the Texas Instruments ADAS Alpha platform. A general diagram is shown in this image, a general implementation diagram, where a frame is loaded, which is in the U of color space, where the Y component represents brightness, while the U and V components represent color. So since the color components are irrelevant, they're suppressed, then the Y components are extracted for processing, Gaussian blur is applied, and then the detector is applied to the blurred image. And the algorithms were evaluated through percentage of differing pixels, mean absolute difference, execution time, and memory usage. For percentage of differing pixels and mean absolute difference, 77 images from the Berkeley dataset were used, along with their corresponding round truth images. And so these histograms show the percentage of differing pixels for the implemented algorithms. So the Canny algorithm has shown the least differing pixels, while the other operators have a higher number of differing pixels due to the high number of pixels in output images, which fall in the 0 to 255 range. On the other hand, Canny also has the highest mean absolute error, which was calculated according to the formula shown here, which is expected due to the binary output image, which results in a high error with fewer differing pixels. And this table shows the execution time range and the memory usage. The Canny algorithm has shown the highest execution time and memory usage due to the additional steps that need to be taken to implement it and the additional memory allocation that was made, while the Laplace operator has the lowest execution time because there was only one convolution step to implement it. And to conclude, the Sobel, Prewitt, Laplace and Canny operators were implemented on an ADAS platform, and possible improvements to the work would be utilization of more than one SoC and to parallelize execution where possible. And thank you for your attention.
I have one question. So which of the presented detectors should be chosen as the best trade-off, let's say, between the edge detection accuracy and the required resources for the computation of edges?
Well, I personally would say that it would be the Canny algorithm due to the binary image where you know that an edge is an edge because there's no in-betweens. And I think with proper implementation, it can be usable in real-time systems.